Good morning everyone. In this video I am going to explain about voltage to frequency converter digital voltmeter. This is an important topic for the students of EEE as well as those who are preparing for competitive exams. Let's get started. A voltage to frequency, VF, converter type integrating digital voltmeter, DVM, is an electronic measuring instrument that converts an unknown input voltage into a proportional frequency. The frequency produced is then counted over a fixed period of time, and the count is displayed as the digital value of the input voltage. This type of DVM uses the integrating principle, which provides high accuracy and excellent noise rejection. In case of ramp-type DVM, the voltage is converted to time. The time and frequency are related to each other. Thus, the voltage can be converted to frequency for the measurement purpose. A train of pulses, whose frequency depends upon the voltage being measured, is generated. Then the number of pulses appearing in indefinite interval of time is counted. Since the frequency of these Pu1s is a function of the unknown voltage, the number of pulses counted in that period of time is the indication of the unknown input voltage. The heart of such integrating type of DVM is the operational amplifier used as an integrator. The input voltage is integrated for a fixed interval. A integration of a constant input voltage results a ramp at the output, the slope of which is proportional to the input voltage. If the input is positive, the output of op-amp is negative going ramp. After some time, the capacitor is discharged to zero, thus output returns back to zero and the next cycle begins. Hence the waveform at the Fig. 2.49 output is a sawtooth waveform as shown in the Fig. 2.49. If the input signal is doubled, the number of teeth in the output signal per unit time will be also doubled. Thus the frequency of the output will be doubled. Thus the frequency of the output is proportional to the input voltage. This is nothing but the voltage to frequency conversion. The sawtooth pulses are finally entered into a reversible counter. The measured value by the reversible counter is finally displayed with the help of digital readout. The block diagram of voltage to frequency converter type integrating DVM is shown in the Fig. 2.50. Each teeth produces a pulse at the output of the pulse generator, so number of pulses is directly related to the number of teeth, i.e., the frequency. These pulses are allowed to pass through the pulse transformer. These are applied at one input of the gate. Gate length control signal is applied at the other input. The gate length may be 0.1 seconds, 1 second, 20 milliseconds, etc. The gate remains open for this much time period. When the gate is open, the pulses are counted by the reversible counter. After gate length period, when the gate is closed, the count measured by the counter is transferred to the digital readout. Mathematical analysis. The input voltage VIN charges the capacitor with a current VIN, R1 up to the reference voltage connected to the comparator other end. Let this voltage as VR. When capacitor voltage reaches this value, the comparator changes the state, giving trigger to the pulse generator. This produces the pulse of precision charge content, which discharges the capacitor rapidly. The rate of charging and discharging results in a signal whose frequency is directly proportional to the input voltage VIN. The waveforms of integrator output and output of a pulse generator are shown in the Fig. 2.51. From the analysis of dual slope technique, but in this type both VR and T2 are constants. Thus the output frequency Φ is directly proportional to the input voltage VIN. The discharging time of capacitor must be as small as possible. Accuracy. The accuracy of voltage to frequency conversion technique depends on the magnitude and stability of the charge produced by the pulse generator. Thus the accuracy depends on the precision of the charge feedback in every pulse and also on the linearity between voltage and frequency. To obtain the better accuracy, the rate of pulses generated by the pulse generator is kept equal to I. The voltage time integration of the input signal. E. The total voltage time areas of the feedback pulses. There are two techniques to design the pulse generator for the better accuracy. I. Using a precision capacitor. The precision capacitor is placed between the pulse generator and the summing junction of op-amp. The capacitor is allowed to charge up to precise voltage level and then this charge can be transferred to the summing junction of op-amp. E. Using a transformer. The transformer can be placed between the pulse generator and the summing junction of op-amp. The primary of the transformer is connected to the pulse generator. The secondary is connected to the summing junction of op-amp. The transformer material has a square-type hysteresis loop characteristics. Due to this, there is excursion around the BH loop of transformer. This excursion can produce precise amount of charge at the summing junction of op-amp. The purpose of the reversible counter is to sense the polarity of input voltage and count the pulses accordingly. If the input signal changes its polarity during a measuring period, then the pulses received by the counter after the reversal of polarity must be subtracted from the previous count. For this purpose, the counter used is a reversible counter. If a reversible counter is not used, then the counter will keep on adding the number of pulses and total count will keep on increasing, though actually the input polarity is reversed. This will give the incorrect reading. This type of situations may occur while measuring the low voltage of the order of MV in presence of a large amount of superimposed noise signal. When the reversible counting scheme is used, there are 4 conditions of counting are possible, which are I. Positive up counting E, positive down counting E, negative up counting IV, negative down counting. For the measurement of bipolar voltages, one more set of comparator and the pulse generator is necessary to add. The second comparator produces positive going pulse for the negative input signal. A plus V volts reference is used at the second input terminal of this comparator. The only important thing is that both the pulse generators should produce same amount of feedback charge at the summing point of the op-amp. Let us study the waveforms at various stages of the DVM when a complex input waveform is applied to it. The various waveforms are shown in the Fig. 2.52. The input voltage has positive polarity for the period T0 to T1 and negative polarity for the period T2 to T4. For the periods T1 to T2 and T4 to T5, the voltage level is 0. The gate should be open for the entire time interval T0 to T6. This is shown in the waveform Fig. 2.52, D. When input voltage polarity is positive, i.e., for the periods T0 to T1 and T5 to T6, the output of the pulse generator is high. For other time period it is low. This is shown in the Fig. 2.52, B. When the input voltage polarity is negative, i.e., for the period T2 to T4, the output of the pulse generator is high. This is due to other pulse generator used for the bipolar voltages. This is shown in the Fig. 2.52, C. For the period T0 to T1, it is positive counting up. For the period T2 to T3, it is positive counting down. For T3 to T4, negative counting up, while for the period T5 to T6 it is negative counting down. Transfer characteristics. The transfer characteristics show the relation between the input voltage and the output frequency. This should be as linear as possible. It remains linear up to a frequency called saturation frequency. This is shown in the Fig. 2.53. The slope of both the positive and negative voltage characteristics must be same. To increase the operating speed of this type of DVM, the upper frequency can be increased, i.e., increasing VF conversion rate. But this results into reduced accuracy, and design cost of such circuit is also very high. Hence, another method in which 5-digit resolution is available is used to increase the speed of interpolating integrating DVM. The block diagram of interpolating integrating DVM is shown in the Fig. 2.54. This is a modified version of voltage to frequency integrating DVM. A zero comparator is the additional circuitry in the DVM. The zero comparator ensures that the charge on the capacitor is zero. During first 20 milliseconds, the operation is exactly similar to the normal VF integrating DVM. However, during this time the pulses are directed to the 100s decade. Here each pulse is equivalent to the 100 counts. After 20 milliseconds, the switch S1 is moved from position 1 to 2 and Vref of opposite polarity is offered. Some charge is still present on the capacitor. The opposite polarity Vref helps to remove the remaining charge at a constant rate. When the charge reaches 0, the zero comparator provides a pulse to the control logic. When the switch is moved from position 1 to 2, at the same time gate G2 is also opened. Hence the pulses from 50 kHz oscillator can reach to 1s decade. When the zero comparator provides a pulse, the gate G2 is closed. This completes the reading operation. If you found this explanation helpful, please like, share, and subscribe to Empower, Aspire, and empower your learning journey.